Hey guys, test on Friday. Here's your review video. I'm going to go over these topics right here. As I go through these, I'm going to make a little check next to each one. So if you see one of them that you need but you don't need the other ones, you can scroll through the YouTube video, find when that spot is about to get checked, and that's when I'm talking about that. So I'm going to come back with all the formulas that you could possibly think about for simple harmonic motion and tell you the ones that you will get and the ones that you won't get. So what I have written up here, these are all the formulas I can think of that you may use on a simple harmonic motions problem. Now, I probably have forgotten one or two. No promises that this is every single one of them, but these are the ones I can think of off the top of my head. This is a lot of stuff. Now, a lot of it we were already familiar with. You know about these already. That's the last test. Most of this stuff over here, old stuff, but we still see it sometimes in simple harmonic motion problems. What I'm really concerned with, you're going to have these. These are both on the formula sheet. But what if you're asked for frequency? You're not going to have the default frequency formulas. Those are not there. This is here. That relationship will be there. This one will not be, I think. Let me double check that. Yeah, I was right. This one will be here. This one will not be here. So you need to realize that reciprocally you can just flip it. That'll be there. That'll be there. That'll be there. This will be here. All the rest of this will be here. That one will not be here. And this is probably the singular most important thing out of simple harmonic motion. The idea that the maximum kinetic energy, same as the maximum potential energy, spring potential energy, or the same as the maximum gravitational potential energy, which is the same as the total energy throughout the whole time. That energy just goes back and forth, back and forth, back and forth, back and forth. This is not on the formula sheet, but you need to remember it. It's just another way of expressing conservation of energy. Now, like I said, I'm probably forgetting one or two of these, so be on the lookout for those. See if it's on the formula sheet. If it's not, memorize it. Ooh, speaking of memorizing, just remember this. For a pendulum, something swinging back and forth, if you have L and you have theta, the height of that pendulum, L minus L cosine theta. Memorize that. You will need it. All right, I have two possible situations up here. These two possible situations could appear in some form using variables. Be prepared for that. The basic idea here is you have some kind of simple harmonic motion thing happening. You need to find the maximum velocity or the maximum height or the maximum compression, some kind of maximum thing. This all comes from the idea, the top right one from up there earlier before I erased it, of that the maximum of one kind of energy turns into the maximum of another kind of energy. So up here, I can write Kmax equals maximum gravitational potential energy. The way I know I'm using kinetic energy, I'm thinking about velocity. It's up at a certain height, which means I'm going to deal with gravitational potential energy. So from here, I just expand and plug stuff in. 1/2 mv max squared. Notice I wrote v max because it was k max. You don't have to do that, but it's very important, I would say. It's going to help you out. And then this is equal to mg h max, which we're trying to find v max. Notice up here I did not give you the mass. You're not allowed to have an answer with mass in it, but masses cancel out. That goes away. We're trying to solve for this. Now this just becomes simple algebra. V max equals 2gh max square rooted. Now, the problem. At the initial bit, I didn't draw that. That wasn't a variable we're allowed to use. So we need to find a way to get rid of h max and only use L and theta. Well, think of that formula you're supposed to memorize. H max, the maximum height of that pendulum, is the L minus L cosine theta bit. So all of this is going to turn into V max equals square root of 2g times L minus L cosine theta. Make sure you put that bit in parentheses. Lots of people didn't on the homework that involved this, and so their answers were a little bit screwy. So now we have a block on a spring. We know the spring constant of that spring. We know the mass of the block. We know how fast the block is going. Using only those things, we're supposed to calculate how far the block is going to compress, the x max. There's this kid, I think you guys know that as A. Same thing. It's the amplitude. Well, we're dealing with motion, so it's kinetic energy. We're dealing with the spring, so it's elastic potential energy. We're going to start off basically the same way we did on the last one. K max equals maximum static potential energy. Then from here, we're just going to start plugging stuff in. 1/2 mv max squared equals 1/2 k x max squared. So some things we need to do here. The 1/2s cancel out. We have a value for mass. It's capital M. We have a value for V max. It's V naught. It's worth pointing out that we know that V naught is the maximum velocity because at equilibrium, the velocity is maximum. That's just an always thing for simple harmonic motion. So I can say M times V naught squared equals K x max squared. From here, it's just a matter of solving. Move K over, square root both sides. X max equals square root of capital M V naught squared over K. To answer the question that some of you have in your minds right now, if you don't plug in capital M or V naught, if you don't plug in either or both of them, then your answer is wrong because you haven't plugged it in, finished. You've talked about the problem in like general terms, but not this problem terms. Make sure you plug in your stuff, even if it seems like you're just changing the letter. Okay, so box of a spring, bouncing back and forth again and again and again. Of course, there is no friction. We're going to ignore that. What I want to talk about is when stuff is at a maximum, when it's at a minimum. So when is it moving the fastest? When is it stopped? When is the force really big? When is the acceleration really big? When are the energies big or small? That kind of topic. Now, everyone, all you guys already have a detailed version of this in your notes. So I'm not going to run through the whole thing. But I want to talk a little bit more about how to think about it, a way to get away from just memorizing it and instead actually like understanding and seeing what's happening. The really easy one is velocity. Imagine this going back and forth. Think about my hand moving back and forth like this. Well, the answers are always going to be either 0 or maximum. So looking at this, it's really obvious to tell where my hand stops. Stops there and there. Stops at the left amplitude and the right amplitude. So velocity always is 0 at the edges. It's going the fastest at equilibrium. So 0, fast, 0, fast, 0, fast, 0, fast, 0, fast, 0. Back and forth, back and forth. What else is related to velocity? You should always be asking yourself that question. See the velocity, base everything else off of that. Kinetic energy. If it's moving really fast, it's got a lot of kinetic energy. If it's not moving at the edges, it has no kinetic energy. What else? Force. You know how springs work. You pull on a spring, big force. No pull, no force. Here, there is no pull. Equilibrium means that there's no pull. So here, there is the force is at a minimum. Here, the force is at a maximum. The spring is squished a lot or stretched out a lot. That creates a very large force. That large force also creates an acceleration. So just like we tied together velocity and kinetic energy, now we can tie together force and acceleration. They cause each other. Excuse me, force causes acceleration. So those are always going to have the exact same answer. Also, notice that velocity and acceleration are opposites. The velocity is very big here, 0 here. Acceleration is very big here, 0 back at equilibrium. They're totally inverse of each other. Another way of thinking about that inverse, kinetic energy, potential energy. We thought about the velocity. Obviously, it stops, going fast in the middle. Kinetic energy is the same way. Potential energy is the opposite of that. We know that simple harmonic motion, just a way of talking about energy being transferred back and forth, back and forth, back and forth. So it's going from maximum potential, maximum kinetic, maximum potential, maximum kinetic, potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic, potential, kinetic, back and forth, back and forth, back and forth. So kinetic energy, potential energy, inverses. But instead of memorizing that, think about the velocity. Observe what it's doing in your mind. If you need to go like this on a test and cover up your and actually move your hand back and forth, you can see it stops at the edges, which means kinetic energy is 0 there, which means potential energy is a maximum there. It's moving very fast in the middle, which means that kinetic energy is a maximum there, which means that there is 0 potential energy there. Force yourself to think through those chains of logic. Get comfortable with them, and you're never going to get one of these questions wrong. Another way of expressing this, instead of seeing a picture like this, is a graph of displacement versus anything. We have displacement in meters, so where the thing is. I could also say the displacement in terms of an angle for a pendulum swinging back and forth, angle versus time or angle versus distance, whatever. This can be time or position, can be anything we want it to be. It's going to look like a basic sine graph. It's going to look something like that. Pardon my not very good drawing skills. It's pretty, I would say, obvious looking at this where the amplitude is. Maximum displacement right there, right there, right there, right there, right there. That's going to be where it stops. Equilibrium, right there, right there, right there, right there. That's where it's going really fast. Another way you can think about the velocity, if we're dealing with the question, is the slope. You guys know what the slope of a displacement versus time graph is. It's velocity. If you have a displacement versus time, think about the slope. Right there, at the top of that line, slope is 0. It's not moving. Right there, slope gets really big. The velocity is at a maximum. So we can either think about it and think, okay, at the equilibrium it stops, so the velocity is 0. Excuse me, at the amplitude it stops, so the velocity is 0. Or we can think about the slope right there. Well, the slope of displacement time at that point is 0. So that 0 slope means that there is 0 velocity, or equilibrium. We know and we can see in our mind's eye that it's moving right there. We can also do it with the slope. So if you get a graph like this, wink, you need to be able to know how to figure out where is the force a maximum, where is the potential energy a maximum, the acceleration a minimum, where is kinetic energy 0, so on and so forth. You should be able to get all of that out of a graph just like this. Linearization is probably going to be the hardest part on this test for a lot of you. You're going to have one out of your 2 free response problems where you are 100% going to have to linearize that. There's no way around it. Here, I have your basic straight line. We have a y-axis, we have an x-axis, we have a linear line. Now, you all can just spout out in your sleep that this is a y equals mx relationship, where you know that y stands for what's on the y-axis, x stands for what's on the x-axis, and the thing in that spot is the ratio of y divided by x. So we call that the slope. Another way, if I ask any of you guys what the slope is, you're going to say rise over run. The rise is the y-axis, the run is the x-axis. Y divided by x. That's how you end up with the slope. That's how we calculate the slope all year. When you did the Hooke's Law lab, you did force divided by x. The slope of that gives you the spring constant. We're going to follow that exact same logic now, but instead of doing it with nice, pretty variables, we're going to have to change stuff. Our slope is no longer going to be m. Our slope might be, I don't know, m squared. All that does is mean there's an m squared right there. Our slope is now m squared. We can take that and do something with it. The slope is no longer the answer with a linearization graph. The slope is a stepping stone. Then you go one step further, and that's your answer. So I'll talk about the lab that you should all be doing right now, the linearization of the mass versus the period of a spring. Now, you're going to do a graph of something, whatever. Before we talk about the graph, let's think about that formula. We need the formula to look like y equals mx eventually. This is our basic formula. What is it? M over k. Period of a spring is equal to 2 pi times radical m over k. Now, the issue here is it's not really easy to see how we're going to graph this. We need to make this look like y equals mx. If we're going to take this and we're going to graph it and get anything remotely resembling k, we need to have the slope have all of our constants and k in it. And then something involving only t will be on the y-axis. Something involving only m will be on the x-axis. Notice how I said something involving? That's because we don't really know what it's going to look like. It can be some fraction of t. It can be t squared multiplied by 7.5. Who knows? Who cares? The point is that we're going to have something that looks similar to this, but is kind of rearranged and shuffled so that it resembles y equals mx. Plus b maybe, but not normally. Okay, first we square stuff. Normally, we wouldn't want to square something like this. Like, I know that this is the step that freaks out a lot of people. Just embrace that freak outness. Don't worry about it. We square both sides. We end up with this. Notice 2 was squared and the pi was squared. So we end up with 4 pi squared. Now, my first period, this just broke them. I don't know why. But realize that's the same if I make it all one big fraction. Or I can say to heck with it, and I can just put k over here. Doesn't matter. It's all multiplication and division. It doesn't matter what order I do it in. Now, looking at this, you probably don't see it yet, but eventually you'll get to the point where you can see it's in y equals mx form. This is going to be our y-axis. This is what we're going to put on the y-axis. This is our slope. This is our x. So if we graph period squared versus the mass, we're going to get some nice linear data. Now, the way I know it's going to be linear, the slope's not going to change. 4 is not going to change, pi is not going to change, k is not going to change. Since all of those things are numbers, not variables, our slope is not going to change. It's going to be some constant value the whole way through. Now, the rise over the run here, that's going to represent our slope, obviously. The rise is going to be the change in period squared. The run is going to be the change in mass. Well, look what happens over here if I do ts squared divided by the mass. I'm left with that. I'm left with our slope. So the slope of this is 4 pi squared over k. But we're not done yet. You've gotten some data. You've squared this data. You've graphed it all nice and pretty. You've made the line of best fit. You've calculated your slope. But now you have to go one step further. Let's say I'm totally making up numbers here, obviously. But let's say that I end up with a slope for this line of 47. 47 units is the slope for that. Well, from there, 47 is not k. 47 is not equal to k because the slope is not k. The k is 4 pi squared over k. So I say 47 is equal to 4 pi squared over k. Well, now I can find k. I have an equation that can give us k. Do a little bit of algebra switcheroo. K equals 4 pi squared over 47. Punch that into your calculator. That's going to give you k. Whatever value you get, that's a spring constant. That's when you're actually done with the problem. Now, there's probably going to be parts after this. We have to do other physics stuff. But this is when you're done with the linearization. You have successfully used linearization to find what you need to find. Let's do one more example talking about the period of a pendulum. This is the lab that a lot of you did today being Wednesday. We have a formula of t pendulum equals 2 pi times the square root of L over G. And in this problem, let's say that I want you to change L, measure the period, and find a value for G. Now, G is a constant. It's not a variable. So we can find it inside a slope. We just need to rearrange some stuff so that it's hidden inside a slope. We need to get rid of the effect of other variables. Another way of thinking about this. Some variables go on the y-axis. Some variables go on the x-axis. All the constants are inside the slope. Linearization is a little bit flexible past that. So, same algebra as before pretty much. TP squared equals 4 pi squared times L divided by G. Well, algebra rules still work. So, now G goes down here just because I say it does. And we have the same relationship. We have this bit can be our y-axis. This bit can be our x-axis, which means the ratio, which is this, of TP squared over L is our mass. So for this graph, we would do TP squared on our y-axis. Of course, we would need a column in our data table where we found TP squared. We would have L as our x-axis, and then the slope would be 4 pi, that's supposed to be a 2, squared over G. So again, you would find this in your data table, get that set up in your data table, graph all that. Your slope is, let's say this time it's 92. Your slope is 92, which means this whole bit is equal to 92. So just like before, we're not done yet. We found the slope. Now we have to go one step further and use that slope to find something hidden inside the slope. We've made ourselves a formula. 92, no, wrong. G equals 4 pi squared over 92. Done. That's linearization. Figure out, based on your master formula, how you need to rearrange that to have a slope that is only constant stuff. Then figure out what your y is, figure out what your x is, graph that, find your slope, then do a little bit of solving, then you're done. That's linearization. Come into tutorials if you struggle with that. First off, you'll need it for your lab. Secondly, you'll need it for your test. Good luck. Last thing I want to talk about, collisions with simple harmonic motion. So something happens, two things hit, and then simple harmonic motion gets going. Now, this is basically another bit of advanced energy, that 5B, because we know that simple harmonic motions is basically just energy, but a different package. It's energy that repeats back and forth, back and forth, back and forth. So here we have two things that are going to hit. We know that if two things are going to hit, our first thought is momentum. Always momentum, never energy. Sometimes we have to do energy a little bit later, but the way we're actually going to understand something here is by using conservation of momentum. This is a totally inelastic collision, which means that we start off with two objects, and the objects stick together. So we can say M1 V1 initial plus M2 V2 initial equals the combination of M1 plus M2 times of V final. Now, notice that when I did this, I wrote it all out. I didn't plug any numbers in yet. I'm just demonstrating that I use conservation of momentum. And then I have to go one further step and plug in numbers. The mass of this object is not M1. It's 3m. The mass of that object is not M2. It's m. The velocity of this is not V1 initial. It's V naught. You need to plug those in just like they were numbers. So M1 is 3m times V naught plus 0. That thing's at rest. It has no momentum. Equals M1 plus M2. So 3m plus m gives us 4m times our final velocity. Well, we have a mass in that term. We have a mass in that term. Boom, boom. 3v naught divided by 4. 3/4 v naught is v final. Now, what I saw a lot on that last test, people would say 3/4 meters per second. Done. It's not 3/4 of a meter per second. It's 3/4 of whatever v naught is. We don't know what v naught is, but it's 3/4 of whatever that is going to be v final. So we're going to keep this in our back pocket and then use it more later. Because now we can think about the oscillation. Because when these things hit, they're going to push the spring in. And then they're going to push the spring. The spring's going to push him back out. Then it's going to pull him back in, then push him back out. They're going to oscillate. And our job is to find the maximum, the amplitude, the maximum x in that scenario. So based off of this, we can think about what kinds of energies are being involved. Well, this is our 0 point for gravitational potential energy. We know that because we say it is. Who cares? We start off with kinetic energy. They're going to hit, and once they hit, they're moving. And then at the end, they're not moving. The spring is compressed, so the spring stores energy. So we could do my favorite formula in almost the whole world. Oh, that's not right. K max equals something else max. My goodness. Maximum kinetic energy is some other maximum form of energy. Now, formula for this, expand, then start plugging things in. 1/2 mv squared equals 1/2, that should be v max, 1/2 k x max squared. Now we can plug stuff in. The 1/2s are going to cancel out. The mass, now I want you to ask yourself, are you going to use m, 3m, or 4m? Answer it in your head. Force yourself to commit to something. The question, the answer I hope you gave was 4m, because this is after the collision and now it's in the oscillation. And after the oscillation, they've stuck together. So this mass is going to be 4m times a bunch of other stuff. V max, well, that's the velocity at equilibrium. Well, this is at rest. The spring's not compressed yet. So that is equilibrium. After they hit, that's the maximum velocity. So whatever we got up here is going to go right in here. Now, I just did one of the most important things on the test that about 170 billion of you missed on the last test. Velocity was 3/4 v naught. So I did not write 3/4 v naught squared. That's wrong. I did not write 3/4 v naught. That's also wrong. The whole thing is squared. You got to square all of that and then distribute that exponent. Equals k x max squared. That bit's easy. No tricks there. Here, I do want you to go ahead and distribute that square and find something with it. You have to square the 3/4 and square the v naught. So we have 4m, square the 3/4, that turns into 3 squared over 4 squared, so 9 over 16, times v naught squared equals k x max squared. Well, now I can go one step further. I'm going to divide both sides by k. I'm going to put all of this over k. And then I'm going to tidy it up a little bit. I'm going to say 4 and 16. Part of that is going to cancel out. And then I'm going to combine the denominators because, remember, it's just dividing. Don't get freaked out. So x max is equal to the square root, am I still in the thing? Yes, of 9m v naught squared over 4k. We had a collision where we did some stuff, and then we had simple harmonic motion, which we explained through energy. If you have any questions on any of this, you need to come into tutorials. Test is on Friday. Remember, it's going to be 2 free response problems, one that's about simple harmonic motion, one that's about linearization and a lab problem. There will also be a little bit of simple harmonic motion on that too. And then 5 multiple choice problems, one of which will be a multiple select. If you're watching this tonight on Wednesday, go to your lab. See y'all tomorrow.